Good afternoon, Tom and everyone. This is our 12th session of the MBT Fireside Chat. We were cut off last time due to a time shortage, and one of the questions you started to answer was only partially answered. And that question was on vengeance and evil. So we'll start with that question first, and then we'll continue on with the other questions. Some of the questions that have been asked today are on physics and science, and these questions are coming from our physicists and scientists in the group. Also, consciousness and evolution, the afterlife, free will, non-physical realms, a lot on dreams, and the ever-popular fear and ego. So let's get started with the first question that we didn't get a chance to finish last time, and that is from one of the MBT forum users. When I see someone do harmful things to other people or animals, I tend to have very negative thoughts which involve harming the evildoer myself to punish them. Where do these thoughts come from? My ego? And how evil are they?
I assume the how evil are they is a question about the thoughts, not about the perpetrators of the horrible things that you're watching.
I think so. I think he wants a definition of evil.
Yeah. Well, we differentiate between good and evil, or between good and bad. I guess evil's just a worse case of bad, but let's just talk about good and bad for now. We differentiate between those with entropy. So if what you're experiencing, what you're doing, is something that lowers entropy for yourself in the system, then that defines itself as good. If what you are intending and doing and thinking is something that increases entropy, then that's defined as bad. So we use entropy basically to define morality. What's good and bad has to do with whether it is helping you evolve the quality of your consciousness and evolve the whole system, or de-evolve and help the whole system de-evolve. So that's how we base morality. And it actually turns out to be a very good way to base morality, because other, what do they call them, morality models or ethical systems tend to base on action. And you can always come up with some actions that, even though they seem despicable from one side, from another point of view, they seem perfectly all right and like they're a good thing to do, and you couldn't do anything else. So we get into these big problems, things that the ethical code seems to be incompatible with itself. It creates, what's the word, conflicts, I guess. And when you talk about it in this sense with entropy, then it kind of resolves those conflicts, because now we're talking about intent, not so much about action. Action flows from intent, but intent is basically the source of the doing, and that's where the morality comes in. All right, so that's how we tell good and evil, and the extent of good and evil is the extent of that entropy increase or decrease. So we don't just have a good and evil. If it's good, it's good. It's evil, and there isn't any difference, So any infraction is as bad as any, as any other infraction. It amounts on how much entropy are you creating, or how much are you reducing? What's your intent leading to? So if this happens and you see something going on and it aggravates you, somebody, kicks their dog, and you want to go over and grab them by the throat and shake them and tell them, don't kick dogs, it's not nice. So that is coming from your ego, obviously. It's I want to go there and grab that guy because I don't like what he's doing. It's an I thing, and it is ego. But how much entropy is it creating? Well, if it makes you really, really angry to the point that, you go ballistic and you go over, or you pull your gun and shoot him, or, you do something like that, all right, then it's worse. You see, now it raises a lot of entropy. You've reacted badly, but if you just see it, you feel that way, you don't really act on it, it just really annoys you and you'd like to slap him or something, but you don't do it, then, okay, it's your ego, it's flared up, but it's not really causing a great deal of entropy increase in the world, so it's not really that bad a thing. It's not that evil or awful a thing. You've just expressed yourself, and the idea that you see that and think, oh, that's not good. There's nothing wrong with that. There's no entropy increase in that. It's the I want to grab him by the throat and shake him. That's where the ego comes in. It's that part of the problem. So yes, you can look at things and say, oh, that was an awful thing. That person is really, not doing well. It's poor choices. That's a bad person or an evil person or whatever because they kick dogs and steal candy from babies. And that's just an observation, and it's a true observation. And if that doesn't create anger or resentment or wanting to get back, then it's not a problem. Now, if you can stop it, if you can go over and say, yeah, please don't kick that dog, or that's my dog, get out of my yard, all of those things are perfectly good things to do. And you should try to protect the weak and keep evil from happening if you can. This philosophy, the MBT philosophy, is not a pacifist philosophy. You don't have to just stand by and not partake. If the guy's continually kicking the dog, you may want to go over and stop it. You may want to get in the middle of it because that would be your responsibility. You see, now if he just gets angry and he kicks at the dog, but he actually doesn't hit the dog, he misses him, and the dog jumps away, which is usually what happens. Dogs are really pretty hard to kick if they're paying attention because they're a whole lot faster than we are. If it's that sort of thing and you want to go over and throttle him, well, you're probably overreacting, you see. And maybe you ought to go over and maybe talk to the guy and say, what's the problem? You seem to be pretty upset here. Is there anything I can do to help? You see, then that would be a very positive entropy lowering way to react to that problem. But if the guy's just nuts and he's kicking the dog or he's keeps stealing the baby's candy or whatever, and you feel like you need to intervene for protection of those that are unable to protect themselves, then by all means do that. And if that ends up escalating into violence, then you should be prepared to deal with that. If you're not, then maybe you should not do it. Not take it that far, or do what you can do. And if it gets past your point to deal with it, back out. You see, you do what you can do, and you're obligated to do that. We take care of things that can't take care of themselves. That's an ethical thing to do. So that's how I would see that. So it depends on if it just makes you angry and you get upset and it gets you up in a whip, then you're losing it. You're losing your cool. You're no longer dealing with it in a positive way. You're letting it upset you. Now you're choosing to be upset and you're choosing to be angry. It's better just to keep your head and deal with it. However, the best way to deal with it. It may be just to walk away and shake your head and figure some people are like that and he's not doing that much damage. He really didn't kick the dog anyway because the dog was jumped out of the way. Or it may be you need to go over and intervene. But that's the choice you have to make at the time depending on what's going on. So if you intervene, then you need to have some skills for intervening. You ought to understand how you can talk to him that will cool him off, or how to help him with his problem, or at least how to defend yourself if it comes that he starts kicking you, after the dog. So you should be prepared for that. That also would be part of your responsibility to be able to deal with things like that, know what your limits are, and don't just make a problem worse, because you could go there and end up just with a worse problem. You haven't actually lowered entropy, you've just made it worse. So that all has to be figured out on the spot at the time, depending on the situation and depending on what happens next. So don't beat yourself up because you'd like to go choke the guy for kicking the dog. If it's just as a thought and you feel that way, and it's not an anger that overwhelms you or the rest of it, if it doesn't interfere with your day, if you don't go home then and holler at somebody because you're upset because the guy kicked the dog. You see, if you don't let it affect anything, and you don't have an intention to get even or, follow that guy home one night and, kick him, that kind of thing. If you don't feel that way, then there's really nothing very wrong or bad about it. It just shows you got a little ego that guy triggered by doing something, and it made you angrier than it should have made you. You should have just, without anger, dealt with it. So I guess that answers that question.
That does answer that question well. The degree of your reaction is what determines the entropy. and the amount of evil. And since we're going for low entropy, we try to keep that minimal. It's hard to control our reactions sometimes.
Well, sometimes you will lower entropy by taking somebody like that who is doing wrong and doing it consistently and stopping them. If somebody is marauding through your neighborhood and they've gone to your neighbor's house and now they're at your house and then they're going to your neighbor's house on the other side and they're just going from home to home stealing things or whatever, and you can stop them, you should stop them, because that is the low entropy solution. Even if that may, even if you take some risk perhaps, and it's a confrontation that you'll have to deal with. Again, you have to be prepared to deal with the confrontation. If you're not, then don't deal with the confrontation. If you're not prepared to deal with it, then you just throw gasoline on the fire. You'll just become another part of the problem. So, you have an obligation to stop things like that. But if it's a one-time thing and somebody just lost their temper and maybe they really didn't want to kick the dog, maybe they knew the dog would jump out of the way and they were just going through the actions to blow off steam and they're not really an evil person, then it's a totally different reaction that you would have to it. Then if you go over and butt in and push the guy around because you're bigger than he is or whatever, you're not helping either. That's also a higher entropy solution. So you just have to figure it out as it happens, what the right thing to do is. You can't say, well, in all cases you need to do this. It's not like that. It depends on intent and entropy, extents, and so on. But yeah, a lot of people get the idea that MBT must be a pacifist philosophy. I mean, it's all about love, right? Well, somebody is kicking dogs or marauding through your neighborhood. Well, you have a pacifist attitude, and you just they'll get their they'll get their reward later, and that you don't have to do anything about it. You just get out of the way. But I don't agree with that, and I'm not that way, and I don't see that there's any point of that. It's about lowering entropy, and sometimes to step in and stop something that's wrong is the low entropy solution, even if that requires violence. But again, if you're going to get to the point of violence, then you need to be prepared for that. Otherwise, you're just throwing gasoline on the fire. So you have to think about what you're doing, which is why the ego getting you angry is dysfunctional. Because if you're angry, then you're not thinking about what you're doing. You're just acting out of ego, and you'll run off and do something, and it may be a great thing to do, or it may be a dumb thing to do. You don't really know because you're not thinking. So that's why the ego part of it is bad. That's why if you let it get to your ego, then you're no longer as capable of picking the low entropy solution and doing it. You've kind of lost your connection with that ability.
The next question is on science. Now, as I recall from the MBT Open Forum at the Space and Rocket Center, this was on October 14th, 2014, you talked about falsifiable experiments. And the question from Adam here is, I was recently talking with a physicist friend about your My Big Toe. He asked me if there were any falsifiable experiments which arise from your theory. I mentioned to him the concept of all movement speed being c or o, and in many years' time, when our instruments are sensitive enough, we could be able to measure this. Are there any other never before done falsifiable experiments which arise in light of your big toe?
Yes, there are. There's lots of experiments. Well, of the type that were done at Pear Labs, okay, but there's an infinite number of those. I mean, it's, they were looking at how does intent affect random numbers. That's basically their thing. And as you recall, if you've looked at my some of my workshops, I talk about the what was it called? The hospital experiment, where we have patient records and how long it took them to get out, and that. Well, you can do that same experiment. It's just a random. That's also a randomness experiment in a sense. It's the same sort of thing. You can do that with a Geiger counter looking at clicks. Two Geiger counters on either side of a radioactive source. They both should get the same number of clicks, and you can bias one or the other with your intent. Those kind of experiments have been done, but Let's assume that they haven't all been done. And one that I proposed in my workshops, if I can remember the details of it, is if you had such an experiment set up, and depending on the different ways that you treat the data and the knowledge you have about that data, you can create all sorts of unusual effects in it. And as I recall, I had hospital data, and I said, well, we break that into 10 pieces or something. And then you can do different things with the various pieces that all came out of the same data set. You can have somebody take an average value of the ensemble of all of them, and then you can take the 10 and do them separately. And you will find that the separate instances where you modified statistical probability all have to then add up together to match what you know about the ensemble. So you've put a constraint, you see, on what you can get out of each separate experiment. So if in the ensemble there was exactly the same number of counts in the left Geiger counter as there was in the right, that was exactly the same, then though you may bias, and then you break that data up into 10 pieces, though you may bias piece number 1 to be lower and piece number 2 to be lower, somewhere along that line, you're going to have to bias some of the other pieces to be higher by the same amount, because we know the ensemble, you see, had no bias in it at all. So you set constraints like that. And there's other experiments along that way that you can set various constraints. So you can take the data and pieces of the data and modify how you get them and what you know about them, which will then modify what you can do with your intent and what you can't do with your intent. And as far as I know, nobody has ever really gone through the trouble, and a place like Pear Lab could do this very easily. They're set up to do these experiments in very, what should we say, very high quality laboratory setting. So anyway, those kinds of things could be done. As far as I know, they've never been done, and it would be a whole array. You'd have to get out the workshop that I did, the one in Calgary. I remember I talked about that for a while and just see what those details were. But yeah, that's an experimental setup that would be easy to test. Does indeed, you indeed keep those structures because of the way you manipulate the known information, and so that's one. There's a couple of other methods that are now being worked by scientists trying to test the idea of reality being virtual, where they're looking for basically signs of the graininess at the at the level of measurement, and whether that graininess is attributed to the pixel size, if you will. They're looking for the pixels in, I think, background radiation or some sort of thing. So there's several of those kinds of experiments going on at the present time. So yeah, there are things. There are falsifiable artifacts. There's lots of people who do healing, use their intent to affect physical systems. They are ongoing. There's probably dozens, probably hundreds of groups that do that. Some are even open to the public, take patients. They are ongoing businesses, and they keep track of records and things. And you could do that to see what sorts of ways that you could manipulate the variables and predict how those manipulations would affect the outputs. So there's lots of ways. If somebody were really interested to go out and do that sort of research to make these falsifiable predictions, then there's plenty of ways that could be done. It's not that difficult. Yes, falsifiable predictions are made. There's not a whole lot of interest in academia to actually go out and do the experiments. That's not a lot of interest there. I had a little talk with who was it? Dean Radin. And we talked of some experiments, but nothing really came of that. these kinds of things. People talk about it, but nobody really wants to spend the money or to do it right with good science. You just can't, have 2 or 3 people over in your living room and, and have a seance. That's not science. You really have to do it in a formal setting with lots of, of data taking and so on. And that takes money, takes people, takes time. And mostly it's not a lack of falsifiable experiments. It's a lack of interest in doing them. And when they're done, like the decades of research done at Pear Labs, nobody cares. You see, they have trouble getting them published, even though their science is perfect. So that's why a lot of people don't do them. There's really no point, because you're kind of walled off someplace that won't get published. People won't take you seriously. And it doesn't matter how good your science is. I know a lot of people have this idea. Science is all about truth. And if you do an experiment and it's repeatable and it shows this, wow, that'll change the world. Doesn't change a thing. Go talk to the folks at Pear Lab, all their PhDs and all their, science and all their protocol and all their error analysis and everything else. And they still can't get published. So just doing the science is more or less irrelevant, which is why most people don't bother, because there's really not much point in it. So yes, lots of stuff's falsifiable. No, not a whole lot of it ever gets out, even though there's tons of it that's been done. You go, look at the, Rhine, J.B. Rhine down at Duke. You can find all sorts of people who have done good quality research that shows that many of the things I say, work the way I say they work. And if you're really looking for that, you can probably find hundreds, if not thousands, of good research that's done that way. And it just doesn't have much of a big impression on the center of science, because it completely violates, conflicts with their central beliefs. Therefore, they're not interested. So yeah, it's not a falsifiable problem, or finding falsifiability is not the problem. Those kinds of experiments have been done for 100 years and done well and good science, and go have at it, but it just doesn't make a big impression on anyone, because it's really not that scientists will go wherever the experiment points. Scientists also, like anybody else, have beliefs, and when things counter those beliefs, you just either ignore them or you deny them, and you go on. So that's the problem.
Thank you, Tom. I remember the interview you did with Dean Radin, and I thought there was some hope there for you two doing some experiments. He said one of the things he said that I loved was that I don't need proof. Proof is about alcohol. I have evidence.
Right.
So I suggest, Dean, if you're out there and you would like to have some more evidence, to get Tom Campbell involved in some experiments. Okay. The next question, also a science question. Can you speak more about the physical concept of resonance? How and why do resonance effects work and happen? This is from Adam.
Okay, well, I would, Adam's here. Tell me, Adam, what you mean, what kind of resonance? Resonance means all sorts of things.
Yeah, I guess what I'm referring to is the transfer of energy from, maybe one source to the next when they're vibrating at the same resonant frequency. So, something like that. You know what I mean? How like, for instance, in your ear, when the vibration comes in through your eardrum, it resonates at a certain frequency, which only shakes a few certain hairs, which then do their electrical impulse. And I'm trying to figure out how you would model these types of resonant effects in like a virtual reality. I guess that's kind of, I don't quite understand how something like that boils down to the zeros and ones of things.
Oh, well, resonance, a very simple example of resonance is that if you have 2 tuning forks and you set them up, say, a few inches apart, and you hit one of them with the hammer, well, not really a hammer, but that's what they call it, a little thing with a ball on the end of it. You hit one of them, then the other one will start to vibrate as well. Okay, so that's a resonance. So you have one vibrating and the other one that's, I don't know, a foot away, even across the room, if it's sensitive enough, it will also start to vibrate. And that has to do with basically the mechanical material properties of the tuning fork and the properties of the acoustic vibration, the vibration in the air. So you have air vibrating, moving back and forth, and you have a tuning fork that just happens to be designed to move back and forth with very little loss, very little energy loss in the system, very little loss to friction, very little loss to heat, very little loss. It's designed to vibrate at just that same frequency. Well, it feels this air pushing it around, so it starts to vibrate too. That's what resonance means. When you have a child on a swing and you push them, they will start to swing. If your pushes are just random, they won't swing very much. They'll just jerk around, on the swing. But if you get it timed just right, well, that's kind of a resonance too. You push energy into it at just the right time, then it adds in the system. And that's a resonance. You can look at the Verrazano Narrows Bridge that ripped itself apart, because wind had its little cables humming. And as those cables hummed, they just happened to pour energy into a resonant frequency of that bridge. And you see this monstrous bridge across Verrazano Narrows. And the whole bridge just tears itself apart because the wind's blowing in such a way that the energy built up in the bridge little by little by little. So you keep pouring it in. It's like the swing. You keep pushing it just the right time. Then you keep adding energy to it because that's a resonant frequency. Well, that's just the rule set. That's just the way the rule set works. So those kinds of resonant effects in the material world they work that way because that's the way the rule set works. I'm sure in the world of Warcraft, you could have an elf and he could hit a tuning fork and have one on the other side of the room, start to vibrate. All you have to do is put the physics in the rule set of World of Warcraft and it'll work like that. So in a virtual reality, if you have rules, if you have a rule set that is our physics, our science, then you get what our science gets. So the reason science works the way it works, resonant effects and everything else, the reason why airplanes fly and all the rest of it is because these are logical ramifications of the rule set. And our physics and biology and chemistry are all subsets of the rule set. The rule set's the superset, right? We don't know everything. We don't know all the physics and all the biology and all the chemistry can possibly ever be known. We still have things to discover and understand. So the rule set has it all. We know pieces of it. And that's all. So the virtual reality just does whatever the rule set tells it to do. Same as World of Warcraft. They have a rule set too. And, that's why the elf can't run but so fast, because there's a rule set. Why he loses hit points whenever he gets hit, because that's in their rule set. We don't have a hit point in our rule set. We don't work that way, but our rule set defines basically energy transfers. How can two things interact? What's the interaction between things? So we have a rule set that defines that for everything, whether it's electromagnetic fields or whether it's a bonk on the head. What happens? And so that's I use the example sometimes, Adam, that if somebody hits you on the head with an iron pipe, then what that does in a virtual reality is that it changes the constraints. And it uses the rule set. Okay, how hard did it hit it? How fast was it moving? Well, it's a virtual reality. So speed and motion and weight and all that's in the virtual reality. That's what the virtual reality is doing. It's simulating all that stuff. So then it hits the skull, and what does that do? What's the tensile strength of a skull? How much does it do? And it goes down into the virtual brain. So it's a virtual skull, a virtual brain. It's all that stuff's just virtual. It's all data, but the rule set can figure how much damage is done and what are the new constraints because of it. Well, then the new constraints are that maybe you slur your words, you drag your left foot, whatever is the result of that brain damage. It's not because there's a brain in there that got damaged. There's a virtual brain, and there's a virtual iron bar. There's a virtual skull, and all of that then is computed, and we come out with a probable damage because it's not all just deterministic. There's a probable damage, and then that alters the constraints that whoever's playing that avatar now has to play under those new constraints. So that's how the kind of what goes on in the physical world, how does it affect, the consciousness and what the consciousness can do. So the consciousness is constrained by the rule set and how the rule set affects the virtual character. That's kind of the interface between the physical and the consciousness, because people will say, well, if you get hit, that's brain damage. So obviously, now you slur your words, or now you can't think, or you don't remember anymore. So obviously consciousness is in the brain because we damaged the brain, and it affects the consciousness. No, it's not like that. You damage the brain. It's a virtual brain with a virtual iron pipe and a virtual skull in a virtual world, and you compute the damage. And that's the same way. And when the elf jumps off a cliff and the cliff is high, guess what? Your elf takes damage. And how much damage? Depends on how high the cliff is. See? So it's the same way. They have a rule set. They compute what the constraints are. Now your elf has different constraints that it had before it jumped off the cliff. It's the same way. Our simulations is an evolved one, not a program one, and it's just a whole lot more detailed. It's a higher resolution, more detailed rule set. So we get very detailed effects.
I got it. Yeah, that it really helped me understand. I think I just had some certain little block about resonance, but I can see now it's just like a material property. If it were like a basic game, right, in World of Warcraft, maybe there's only 10 frequencies, and say he casts a spell at one frequency, well, that tree has that same material value, so it has more of an energy transfer, like less loss of energy, right?
Right. It's just the rule set. It's just the way the rule set's made. And it's just ramifications of that rule set. That's all. Things happen in this virtual reality because that's the way the rule set works, and because of past history. You always have initial conditions, and then you have a rule set, and then you have an output. And then the consciousness isn't in that reality. The consciousness is in other relative to that reality. The consciousness is non-physical. It has to be. And it's outside playing a virtual avatar that's interacting with other virtual avatars and with the environment. So we can jump off a cliff too. We can go up and jump off a cliff, the same thing. It computes probable damage, and then that's those are the constraints we live with. And if it terminates us, well, then that's another constraint we live with, right? Then we're done. We have to go get a new avatar. So that's the way it works. And the reason why the consciousness can't be in the same reality as the avatar is that a simulation doesn't simulate itself. It has to be simulated outside of itself. So the elf looks around its elf world in World of Warcraft. The server world, where the server is non-physical to the elf. The elf's world is in his map, right? It's the trees and ground and rivers that are simulated in his virtual world. The elf would look at that and call that physical. That's his physical world. And the server is non-physical. And the player is non-physical. Of course, the player is the elf's consciousness. Whoever's playing that elf is the role of the elf's consciousness. So the consciousness and the server both have to be in the same reality frame because they communicate with each other all the time. The player sends data to the server sends data to the player. They have to be in the same reality frame. Okay, but the elf is in a different reality frame. They can't be in the same. So here we are in this virtual reality. We think we're in this virtual reality. It's just our virtual body and with our virtual brain and a virtual cliff and a virtual river and virtual storms, and we have all that. The rule set's calculating what those interactions are, and we, the consciousness, are not in that frame. We're just playing a character that has different sets of constraints based on what's going on with all these players, which is the same way it is when you play World of Warcraft. You're a player, you get a data stream. You're not in the elf's reality. You're sitting in a chair with a computer in a different reality frame. You're non-physical to the elf. And you get to play with however the interaction is with all the other players and all the other stuff. So you fall in a river, you might drown if you don't get out of it until, you know, some other big player comes over, it's more points than you, and, you know, knocks you down or steals your gold or does whatever might happen. Well, that's constraints now that you have to live with. That's the way it is here. It's a multiplayer game. So the consciousness is always outside of the virtual reality. So that's what we are. You kind of have to think of ourselves not as bodies, and not of bodies with somehow that has a consciousness stuck inside our head. You see, you have to think of ourselves as a consciousness. We're in some other reality frame altogether, but we're immersed in this experience of this virtual reality with our particular avatar. And we're doing that so we have choices, and those choices help us evolve. So I don't know if that helps, but I've tried to kind of outline what the basics are there so you can keep the reality frame separate. What people tend to do is mix those reality frames up. They want the consciousness to be in the virtual frame with the body because they like the idea of consciousness living in a body. So they want to stick those two frames together. And then they have the server someplace else that's now downloading, information to the consciousness that lives in the body. And you get all this kind of extraneous nonsense because we don't keep the various reality frames separate. So that's, we try to make everything physical. We want everything to be physical because that's just our cultural beliefs. So it's what gives us that's what makes it hard for us to understand is our cultural beliefs. And every time we think of it, we kind of get hung up on this idea of it being non-physical or virtual reality. It's a difficult thing for people to grasp.
All right, Tom. Adam has another question also on physics modeling and simulations. He asks, can you speak more about your career in physics modeling? What were some of the procedures you would use to model things in your final years of work? And did you work in any particular multiphysics software programs?
No, I didn't work in any particular software programs. I created all my own software programs. The problems that I worked with were unique problems, and were totally different. Every one was very different than the other. So basically, I created software models, and typically the way it worked, I would write the algorithms. I'd do the physics and write the algorithms that explain how things worked and how they interfaced and interacted and what did what to what. And I'd have 3 or 4 or 5 programmers that I would keep busy that were taking all of those algorithms and actually putting them into code. That's kind of the way I worked. So some of my first things that I did was I worked a lot with electromagnetic systems. Say, for instance, radar systems, electromagnetic fields, near field, far field, servo systems, that kind of thing. And I did modeling. So in this case, people wanted to know 2 things. One, here was a system that your adversary had, and here's how it worked. How could we beat it? How can we jam that radar? What can we do to its, to its antenna and to its receiver and all that electronic stuff in there to make it wander off target? Okay, because it had a technology that was, quote, theoretically unjammable. Okay, so when you have technologies that are theoretically unjammable and you still need to jam it, then you have to understand the details of what's going on so that you can help build up noise, say, in the process. And you need that noise to be cumulative. Again, like a resonance, you need to get something, affect it from the outside in a way that the noise becomes resonant with what you're doing, and the noise starts to grow, and pretty soon they don't know what they're doing anymore. So it required a lot of detailed knowledge of electromagnetic fields and processing and that sort of thing. And I modeled all that in a computer. So I modeled, the radars, the antennas, the electromagnetic fields, the other antennas on the other side that were receiving it, the electronics, all the circuitry, all of that had to be modeled so that you could then experimentally, modify certain variables. Well, what if you send a signal in like this? What would happen? And eventually, in fact, that turned out very well. We did find a way to jam the theoretically unjammable system. So that's the thing. And then, of course, the flip side of that is, oh, well, that's how these unjammable systems can be jammed. We have a bunch of those too. Now, how can we protect ours from somebody doing the same thing to us, you see. So it worked both ways. And that was kind of one of the first models I did was, and I probably spent a couple of years modeling in mainly electromagnetic field theory, was what it did. I wrote a couple of papers in field theory when I did that. It was pretty interesting. Anyway, I'll just jump, things, that kind of thing is what I did. So that, it's not like there's a program that does that. You just have to sit down, understand electromagnetics from basic principles. You start with Maxwell's equations and you go from there and start modeling mathematically what's going on. And I mentioned the last one I did, well, it wasn't really the last one, but near the last one I did was probably one of the most fun off the wall things that I had done. And that was a analysis that I did for NASA. I did several things for NASA, but this was the one that was the most fun. And that was, they wanted to know what was the probability that their launcher, their rocket, it would be their space shuttle plus the booster that gets it up off the ground, would run into a bird. Okay, now that sounds silly and you think, well, it would just smush the bird, but that's not so. When you are going Mach 2 and you run into a 4-pound bird, that's like you're sitting still and a 4-pound object is being hurtled at you at Mach 2. In other words, that's like standing in front of a very large cannon and having it, go off and hit you broadside. So the kind of energy exchanges that even a medium-sized bird, as it hits that shuttle rocket going up, you're talking about millions of pounds of force that are delivered in those impacts, not because the bird is flying so fast, but because it doesn't matter which one's flying fast. It's only as long as, one of them's flying fast, you hit you get a collision between the two, and it's irrelevant which one. So, it doesn't matter whether the cannonball hits you at, Mach 1 or whether you hit the cannonball at Mach 1, makes no difference. The collision's all the same. So it's a very serious problem, because if you do run into something like that, then it'll rip all the things off the side of your missile. It'll break through into your tanks. All your oxygen and fuel gets scattered around. It's a disaster. It kills everybody on board. So it's not a minor thing. And they had a few of their flights, mostly test flights that they had done earlier, unmanned flights that NASA had done. They just went up and kind of blew apart, and they had no idea why. And one of the underlying causes was it hit a bird. Now if you hit the bird in the first 2 or 3 seconds, no problem, because you're not going very fast. But if you hit one, these things accelerate dramatically, and it doesn't take very long before it's going fast enough that even a medium-sized bird will basically destroy the whole rocket, rip it apart, break things up, rip off antennas, cause you, critical damage. So anyway, a little piece of foam broke off once, right? That was just a little piece of, that's a little piece of foam. I don't remember how much it weighed, but it was in around the 1 pound, 2 pound piece of foam. And it was a disaster for that shuttle because it bounced off once. So, and that was kind of early on. That even wasn't at the really high speeds. So you can see it's a problem. And they've had some, like I say, go up and just disappear, blow up, no reason. Nobody could figure out exactly why. They always come up with something in their report, but there was a lot of uncertainty about it. So they wanted to do this, but nobody had a clue how to do that. So I got the job, and what I had to do was model not only the rocket, of course, all the pieces and parts on that rocket, all the materials, but I also had to model the birds. Where are the birds? What season is it? What time of year? What birds migrate over that area, so that I could come up with a probability. Not only that, at what altitudes do they migrate? Because if they only migrate close to the ground, then we don't care, you see. And what flies high? And how high do they fly? And you'd probably be surprised to know that birds fly at around 30,000 feet sometimes. And we gasp at that because that's, minus, minus 50 minus 60 degrees, and there's almost no oxygen there. How do they do that? How do they survive? We couldn't survive at that altitude, but they have evolved to do that. And there are some that fly in those kinds of heights. There's several species that migrate over Mount Everest, which is just about 30,000 feet, you see. And so there are problems like that. And I had to understand how the bird and the rocket would exchange energy. How does a bird smush? You have to deal with things like beaks and bones and stuff because they have a totally different impact than does stuff that squishes like flesh and liquids. And what's the coefficient of friction between the two? And depends on the angle that it hits. And you see, there's lots of things like that. Is your energy transfer between the two things has a whole lot of variables in it. And coming up with the proper statistics and the proper modeling of the energy exchanges of the birds in flight, where they would be, and the rocket, its trajectory, what angles would it be at, all that sort of thing, was a big job. So it took about a year to pull all of the data and information together and write an awful lot of code to all the dynamics of that, get the data on the probabilities of everything happening. And that was just fun, something I'd never done anything like that before. I'd done a lot of other things that were similar, but that was just a kind of a fun, interesting program to do. And I had 2 or 3 programmers working for me, and we produced a really nice piece of work that, interestingly enough, when we did the statistics on what's the probability of all the rockets NASA had launched, what's the probability that they would have been hit by a bird strike? And the number came out to be very, very close to the number of those rockets that just blew up for no good reason. So there was a data point that said, okay, it was a pretty good model. Plus we had some other data points where airplanes and other things had hit birds, and we took that data. You'll probably find it funny to know that there is an installation in Tennessee run by the Air Force that has a chicken cannon, and they actually fire chickens at plastic canopies. So that, not live chickens, no cruelty. I think they buy the chickens at the supermarket just like everybody else, it's just a chicken carcass. But they have ways of accelerating the chicken through a chicken accelerator and slamming it into a plastic canopy because the airplanes have the same problem. And, militarily, you have your best attack if you can fly fast and low, because that gets you under the other, your enemy's systems. And when you fly low, you're in bird territory. And if a bird hits your canopy and kills everybody and takes out your plane, well, that's a $5 million plane destroyed by a pigeon. That's not a good idea. So flying low and fast is a tactical advantage, but not if you have other vulnerabilities. So the Air Force needs to know how to make canopies that don't break, and that don't damage the outsides, don't damage engines. They have to make engines to spec of, how big a bird at what speed can that engine digest without not working. So it's a major problem. Airplanes go down at the airports every year. There's probably a dozen airplanes that crash on takeoffs because they ingest birds. Because for some reason birds like airports, big flat grassy areas and lots of worms, I guess, and bugs. And so yeah, it was a interesting. You can see I've been digging around in this database a little bit. It was pretty interesting. So I did a little bit of everything. Basically, as a consultant, I'd get called in to solve a problem that nobody in-house knew how to solve, and that it was going to be enough trouble and take enough time that they really wanted to pull somebody else in to do it. And my specialty was doing risk analysis, for large, complex systems. So that I got pulled in to do that particular one. And that one was just fun because it was different. So that's just a little smattering of things I did. I've done all sorts of things, but those that was kind of in the beginning and at the end, and everything else in the middle was kind of between those two. But mostly it's just technical stuff that you have to write the equations of how does the stuff work, and then see how it comes out, because the systems are so complicated you can't just look at it and say, oh, if this happened, then that would be the result. That's easy if your system's simple. But if your system has 6 million parts, by 5,000 different contractors, and lives depend on it, then you can't look at all of those thousands and thousands of interfaces and say, well, what if this part failed? What effect would that have on the whole? Well, sometimes not at all. Sometimes it's a disaster. But sometimes the disaster only occurs about 5 levels down through the interaction. This part went bad, so it affected that part, which made that part unstable, which affected this other part. And this other part then, wobbled a little bit, which, gave it a 5% probability it would affect that part. And when that part goes, the whole thing blows up. You see, there's chains of logic that connect everything to everything, and finding the risks. What can go wrong and what's the probability of it going wrong, you see, is the key, because then they want to fix all those things that have a higher probability of going wrong. That's where they want to put their money. And the stuff that it doesn't matter, well, if that goes wrong, then okay, this isn't as warm as it should be, but it'll still work. Well, we don't worry about that too much. The things that can go wrong, that are serious, we have backups for them. So if they go wrong, there's something else to take their place. Or we have ways that we can keep that causal chain from, we break the causal chain someplace before it gets to disaster. So that's what I do. That's what risk analysis means. And I do computer modeling because that's the only way to do these things. The other way to do them is to actually fly the thing, do it with real things, take a real missile, and hit it with a bird, you see. But that costs many, many millions and millions of dollars, and nobody wants to do that. So what we do is we do computer models of it. We model it and then modify change the variables and see what happens. So that's been my life as far as physics goes. It's a traditional Newtonian physics, applications of basically Newtonian physics. I don't get into quantum mechanical things, and I don't get into the speed so high that relativity is an issue. It's a Newtonian application to real world problems. Probably more than anybody wanted to know about what I do at work, but there it is anyway.
No, that totally fascinates me. You can just model the whole, the rules of the reality on a computer now, and you can get super accurate results. I mean, just if there's another data point in, to kind of show the virtual nature of things.
Yeah, well, you have a big computer model, and the computer models, you look at the stuff that you need to know in a lot of detail and high resolution, and you look at the stuff that you really don't, and you model it differently, so you have real detailed models, real high fidelity models with some parts of it. And then you just have interface models that are real cheap, maybe statistical models on the outside with the other stuff. And you kind of, you're always constrained by how much computer power you've got. Now, that first problem I was telling you about with working with that jammer on a unjammable radar, my computer runs would be sometimes 2 and 3 months long. That's how long it would take the computer to come out with an answer. Yeah, no, that's insane, right? I mean, who does a computer run that the computer sits there and chugs for 3 months before you get a number out of it? End of 3 months, you get a number, that calculates what's going on. But that was 1973, 74, early 70s. Computers then, even fast ones, weren't nearly as fast as our desktops are today. And these equations are very complex, and it just took that long for the thing to run. So they had a check something restart, checkpoint restart was the software they were using, so that my jobs would run in the background all day long, and they'd run all night. I'd run all 3 shifts, and on night shifts, I'd get all the computer. Day shifts, I'd get background. And they just run and run and run until they were done. Now, that's the problem. If you make a mistake and you go, oh, I just got this thing out. I waited 3 months for it, and I forgot to dot this I, Oh, I put the wrong number in here, you see. Well, that's why it was very important to do them right, you see. So doing them right and not having errors and so on was a high premium in those days. So it is a big deal, and you have big programs. Now, the ones that I was doing for NASA, that bird thing, Eventually, we got it broken all into matrix math, which is was run by a piece of software. You asked about software. What was it? The matrix machine, MATLAB. Okay, MATLAB. That's what it was. Yeah, we ran it in MATLAB because we put the whole thing into matrix form, and it would run in about 20 minutes in a matrix form in MATLAB. So see, that wasn't so bad. And without the matrix form, before we did that, it would run in about 2 hours in MATLAB. MATLAB's not very fast if you don't take advantage of its speed, which is in matrix manipulation. So, and the reason we did that is because the guys that programmed for me, that's what they did. You know, that's a tool that a lot of the kids coming out of school know how to use. They had that tool handy, so that's what they did it in. I let them worry about the hardware and the software part. I just write the algorithms.
Cool. It's cool. Very cool.
Thank you, Tom. That was really fascinating. The next question is on the larger consciousness system. Now, we've pointed this out before in an interview. Not only can you analyze, or did you analyze for NASA, the large complex systems, you did risk analysis for that, but you can also explore the what you call the larger consciousness system. The question here is, what stuff is the larger, this is coming from one of your MBT forum users, what stuff is the larger consciousness made of? I'm no doubt the right stuff, huh? But he also says, if it's data, then what is this data made of?
Well, what is the elf made of in World of Warcraft? Same answer. What is that elf made of? What is that tree made of in World of Warcraft? What are those rocks made of? What are those people made of? You know, it's information. What's the information in a computer? Ones and zeros, right? I mean, if you want to get down to, you know, the bits, then the information is coded in bits, but that's just the information's coded in the bits. Information itself is non-physical. Bits can be physical. You know, bits could be ones and zeros. They're little charges on a transistor inside of a memory. So, you know, that's a physical thing. So if you want to know, you know, that, then, you know, you go to computer science. They'll tell you what a 1 and a 0 is inside the machine. It's typically a transistor that's either on or off, you know, a conducting or non-conducting transistor. That's why they talk about chips with, you know, millions of transistors on them. Those are little switches that are ones and zeros. So that's it. It's just information. It's the same thing, you know, the same stuff the elves made out of. Same stuff World of Warcraft and the Sims are made out of. It's just information. And where do you get the information? The server sends it to you in a data stream, right? It sends it to your computer. You log on to the game. That gives the server your address. You and the server for World of Warcraft are now connected. The server sends you data. That data lights up pixels on your screen. You look at that screen and you interpret it as the World of Warcraft map. That's how it works. So you get data and you interpret it. Now, you're a consciousness, let's say, and you're playing an avatar in this physical matter reality universe of ours, which is a virtual reality, just like the World of Warcraft virtual reality. You are a consciousness. We just went over this earlier, that you're not in that reality. You have to be outside of that reality, and there has to be a server creating that reality. Well, the server creates the reality. It sends you a data stream. You get the data stream, and you interpret it. It's the same thing. So you are a piece of consciousness. As far as this physical universe goes, you're in other. You're in some other reality frame that's non-physical to this virtual reality. You're getting a data stream from a server that's also in other, and that server is creating information, creating data that you interpret as this reality. That's how World of Warcraft works. That's how this virtual reality works. There's nothing more to it than that. So you as consciousness are just getting data and sending data. You receive data from the server, and then you give your avatar a command, just like you tell your elf, fight, run, sit down, stand up, dance, look left, look right. You have to tell your elf to do those things, or the elf just stands there and doesn't do anything. Well, your avatar's like that too. If you, the consciousness, don't give it any instructions, it just stands there and doesn't do anything. So that's the way the game works. So what stuff is it made of? It's just information. Made of the same stuff the elf's made of is what your body is made of. Information in a server.
Tom, would you say this information is consciousness with intent?
Well, the information, you see, okay, maybe I have to back up one more step or go up one more step. The computer is the larger conscious system. Okay, a subset of the larger conscious system is what the server is. We're talking about the server. So are you a subset of the larger conscious system? So you are a subset of the larger conscious system. I call that an individuated unit of consciousness. The server is a subset of the larger conscious system, and the server is there to create the virtual reality. So you, the consciousness, have choices to make that enable you to grow up faster than if you didn't have those kinds of choices to make in that kind of a reality frame. So that's kind of how it works. It's the server, which is the larger conscious system, just a information system, if you will, and you can call it a computer if you want to, but it's an aware information system, and you're a piece of it. The server's a piece of it. Other virtual realities are also computed by it. See, a virtual reality is just a rule set. It's information abiding by a rule set. So you have the Sims. They have a different rule set than World of Warcraft. You don't have hit points in the Sims. It works differently. So you have a different rule set. Although both of them don't fly through the air, both of them have gravity. Both of them can't walk through doors. There's a lot of things that are similar about it because they mirror it after our virtual reality. So virtual reality is just information constrained by a rule set. So I don't know how to answer that question. What's the stuff? There is no stuff. It's data. What's data? It's ones and zeros. It's information. It's code. And how does it turn into an elf or a human being? It's how we interpret it. It's how we, the consciousness, interpret the data. That's what makes the elf an elf. How we interpret. Why do we interpret it that way? Because when we connected to that, when we as a free will awareness unit connected to that server for the first time, we came with no history. We came with we came with nothing but a potential of our parent individuated unit of consciousness. And we connect to that server, we started getting information, and we don't know how to interpret it. But there we are. We're getting information, and we learn to interpret it just by, being involved with it. So you're an infant. Maybe you're not born yet. Maybe you're 3 or 4 months out of being birthed, and you're starting getting sense data. You see light, you see dark. Oh, there's this nice punching bag in front of you, that you can, do your karate kicks and punch mama in the belly from the inside, you see. So there's all these things that you can do. And if you have choices, then you can make those choices. And then you get born, and then you have experiences, and you figure out, what are the other entities here I'm involved with? What is all this stuff? How does it do? How does it relate to me? And you learn how to interpret it, because you don't know otherwise. And then by the time you get to be 14 and you're playing World of Warcraft, you look at it and you say, humanoid shape, green, pointy ears, an elf. And there's a tree, there's a house, there's a rock. You know all these things. You know how to interpret it because you learned it from scratch. So that's how you know how to interpret it. Well, it's the same. You're a consciousness, and you come basically unable to interpret data at all. You start getting a data stream from this physical matter reality server, and you start learning how to interpret it. And eventually you interpret it like everybody else does, because it's a shared thing and a shared reality. And mom from dad, a house from a wheelbarrow, you learn all these things and words and language, and all the rest of it comes with experience. So that's how you know how to interpret it. You figure it out from the ground up. Every time you figure it out again.
That was really good. That data defines the interpretation.
Yeah, well, the consciousness defines the interpretation. You know, the data is what we interpret. And then the consciousness gets the data. And I did a paper where I defined a lot of terms and passed it around. I don't know if you've seen that or not, but in there, I actually make a discrimination between data and information. Data is just the ones and zeros. That's the stuff the server sends to you. But a consciousness has to interpret that data, and when they do, that's information. See, so there's a difference between the data, which is what you can encode information in, but then somebody receives that code, they have to take that code, which is data, and reinterpret it into information, which is their understanding of what it means. So a consciousness is required for information. There is no information without consciousness. There's only data. Consciousness interprets it. So the information is the meaning, the content, the significance of the code is the information. Just a bunch of ones and zeros doesn't mean much. But when it's displayed on your screen as little pixels that you can interpret, well, now it's got meaning, you see, but it takes a consciousness to interpret it. That's why your computer isn't sitting on the side watching you play World of Warcraft, you know, interpreting it as elves and the rest of it. You know, it's just data. It's just ones and zeros. That you are the consciousness. You get to interpret it as an elf and a tree and a woods, you know, and a lake, because that's how you've learned to interpret those kinds of pieces, little specks of light that you have on your screen. That's how you interpret those pixels and those patterns. And you interpret it that way because you grew up figuring all that out.
Okay, Tom, that very well defined it. Lawrence had a question. Could information be non-physical possibilities within consciousness? For example, consciousness has non-physical possibilities converted from mind.
I'm not sure I got the question. Lawrence, you want to explain that?
We'll let Lawrence do that.
Yeah.
Sure. I was wondering if the possibilities, like when they said that what was consciousness made of, I was thinking that maybe consciousness has unmanifest possibilities within it, like a subconscious, and then when it evolves, those unmanifest possibilities become manifest within it. Like when you said the consciousness itself is evolving, so maybe like it has these possibilities like mind, body, spirit, soul, and that these possibilities could probably mean something in our world, like body is space and time, mind could be dark energy or dark matter, soul could be quantum mechanics, and spirit could be like the information realm. And then so like when consciousness evolves, space just begins expanding within itself and just continues that expansion. So like these so really could the possibilities just be like non-physical unmanifest possibilities within consciousness, that when it begins to evolve or manifest, then those possibilities become information to the consciousness. It begins to manifest it and therefore become information to us.
Okay. Everything, of course, starts as non-physical, possibility, right? If we talk about the larger conscious system evolved from just a very simple awareness that could be in one state or another, right? And then from then on, it evolves to where there's multiple states and then patterns and then time and so on. It keeps evolving, and it's still evolving. It's not a system that's done. And yes, all of the things that it might do, digital systems are hugely flexible. They can just do all sorts of things in many different ways. They have all these neat properties because they can always delete, back up, they can pull things out of memory that are old and start working on them again. I mean, they're not like us. They're kind of very linear and limited. Digital systems are wide open with lots of potential, lots of possibilities. And the system basically chooses to do those things or to manifest those possibilities or to work with them if they help it survive, if they help it lower entropy. So I think it's the lowering the entropy is the key thing here. It does what it does in order to lower its entropy, which means survive rather than return just random bits. The things that it does have to be meaningful. That's information. So it's just bits scattered in interesting patterns isn't enough. You know, it has to be meaningful. And as much as it's meaningful, it's creating information. Again, it's not the bits. The bits are really different. The bits are code. Information is the meaning and the content of that code. So it has to keep making information. And however it does that, now it found out that a virtual world like ours was really good for making choices, because the choices had feedback, they had substance, they had consequences. You do something and there's consequences, and then there's consequences of the consequences, and that all just feeds downstream. So you can look at long-term consequences of things that happen today that will still make a difference, 20 years from now, that kind of thing. So you have this feedback, this continuity, this context, and that turned out to be a really good idea, because consciousness can come here and make decisions and grow up much better than it could just with nothing but communication. It didn't have any other context other than just words passing back and forth, or ideas passing back and forth. So yes, it evolves into that which supports its purpose, which is to survive and grow. That doesn't mean that there weren't a whole lot of other things that it might be able to do that it hasn't chosen to do, or there may be better ways for it to learn and grow that it hasn't figured out yet. So it's just an evolving animal, an evolving critter, an evolving entity, as we are. And there's probably many different branches or paths that it could explore. And I guess it explores those mainly. One, first it has to think of them, and two, it has to implement them, and three, it has to lower entropy, or they're wasting their bits on it. So that's kind of why it is we manifest what we manifest, and there's bound to be huge amounts of potential and things that could happen that never manifest because they don't end up decreasing entropy, or not effectively.